Working all right. Yeah.
Great. Well, I'd really like to first thank the organizers of this online workshop. It's a great opportunity to do this. This is actually a talk that Jim Wenner was planning on giving at the March meeting, or much of this talk is based on that. And so to have an opportunity to come together as a community and discuss these issues, which we can see are making a lot of progress, but there are also a lot of active development that is occurring. It's great to have this chance to touch base with the community.
Is Jim here?
Yeah.
Hi, Jim. We miss you. That's all.
Yeah, just Jim got his degree at UCSB. For those who know. Oh, hey, Jim's on.
Hey, hi. Thank you.
Yeah, so it's good that we have lots of good connections amongst this community. I'm sure not all of them are through Yale. All right. So again, just thanking the Army Research Office. I learned a lot from my Northrop Grumman colleagues, including Jim and Mo, who did these experiments that we're going to talk about, and then of course all of my other Silver Bullet teammates that I work with as part of a multi-institution program to develop noise immune qubits. So basically, this picture shows that the variant of the 0-pi qubit that we've been working on at Northrop Grumman. And there are, as we've heard today, there are a lot of different approaches to this particular type of circuit, and we thought that we would try a variant that emphasized two important parts. One is that, and this is actually in line with the original proposal of what 0-pi was all about, was to make a Mobius ring where you have these large capacitors that define the much of the capacitance matrix of this circuit. And sort of instead of having just one or maybe two big capacitors, you have a whole ring of big capacitors. And the second major element is that we wanted to really explore the tunability of the circuit. So all of the junctions are compound junctions, and we can simultaneously tune them. We call that the global alpha flux. And then we have one junction which we can tune individually. We call that the local alpha flux. So Northrop Grumman also works with Lincoln Lab, and you guys heard a lot about the great flux qubits development that's going on there. So a lot of the intuition that I have, at least, comes from tunable variants of those flux qubits, and for and these kind of high coherence annealing operations that kind of inform a lot about what I'll be trying to talk about. But this will be at a very caricature level, so I hope the general gist of what it is we're trying to accomplish comes across. So just to kind of, again, to talk about the schematic of what is the physics of this particular type of device. So because the loop inductance of this ring is so large compared to individual junctions, that you have actually multiple minimums of the potential that are stable current carrying states. And you can index them by an integer m that is proportional to this amount of current that's flowing in the loop. So we also have, in addition to these biases that bias the compound junction, we also have the ability to bias the overall flux through the loop. And that's, here I've only shown it tilting the middle two wells, but in fact it kind of tilts the entire quadratic potential by using that delta flux. So those are the three fluxes that we utilize to bias this qubit up. So as you change this local alpha, what is its effect? So its effect basically can be shown or thought of schematically as raising or lowering the barrier between the two lowest wells of your circuit. In fact, it can provides a tunneling pathway between all wells, but you can kind of think about it in certain regimes as being modulating this barrier between them and allow variable amount of tunneling between these two wells. And in particular, it allows the tunneling between states that are separated by a change in your vortex number by 1. So that's a critical point. Of course, we also have this separate operation where we can simultaneously put flux through all of the compound junctions at the same time, and this lowers the overall harmonic energy of the entire quadratic potential of the potential. So it basically costs less energy to have different amounts of integer flux in the overall loop. So one of the key aspects of why do you want to have all of these capacitance, how do you want to arrange the large capacitance in your circuit? So, and I think this kind of goes in some ways to answering John's question at the end of Andrew's talk, is that what you're really trying to do is to arrange the capacitance in such a way that you dramatically suppress the tunneling between wells that are separated by a change in this m number by 1, by the, you can say it as the number of vortices by 1, but still allow strong coupling between minimums that have changes in vortex number by 2. Okay, and so it's that kind of T1 suppression that you get from having your two qubit states in your even and odd sectors, but then you have a strong delocalization over the between within the even sector and the odd sector. So you kind of have this kind of like dual notion of separation in one degree of freedom and delocalization in the other in another direction. So how are we trying to validate whether this capacitance structure is adequate to kind of allow this kind of vast separation in scales between what I would say the single vortex hopping physics and the double vortex hopping physics? And one way that you can do that is by looking at just the overall excitation spectrum of the entire circuit. So you don't put any flux into the circuit, and you basically just kind of see, well, there I have rotational invariance, and I can kind of think of what the normal modes are, and you can just do a classical normal mode analysis of what excitations you should see. And what happens is that the odd modes that kind of create voltage fluctuations on opposite sides of these big capacitors, they are dramatically lowered in frequency, but the even ones stay very high in frequency. And so as you kind of reduce the overall critical current of the entire system, it's going to be even type processes that are first turned on, but they'll remain exponentially dominant over the all odd processes. And when you switch your vortex number by 1, that's always an odd process. And so those get suppressed, but even processes, 2 vortex hoppings, are not. So this is one of the very first things that we saw in this system, is that indeed we were able to map out the spectrum, and we saw the types of spectrum that we anticipated would be there. So we had high confidence that this kind of Mobius connectivity was indeed working. That's one of the things that you always imagine is, first time you get a 3D printer, can I make a Mobius loop out of it? So here is our way of validating that, yes, we were able to make a Mobius loop. And another thing that we did is that we, at the upper sweet spot, we wanted to probe as a reference the T1 and T2 times just when the qubit is basically in a microwave regime. And so where the information hasn't been encoded in any special way at all, you've just kind of changed the local alpha bias a little bit to kind of split the 2 lowest frequency modes, and then you can just kind of address these with microwave in the regular way, and you can see that the noise power part is nothing to write home about. These are very short frequency qubits. But the real question that we were trying to answer is, can we suppress the sensitivity to that noise with this clever design? So another critical thing that you need as part of your arsenal, or there are other ways that you can do it, and Andrew did a good job of kind of discussing how you might want to do operations by getting excitations really high up into the energy and then kind of have it come back down again. But what we're trying to do in this case is to basically just use all this flux controllability of these circuits to modify the qubit in real time and let it adiabatically adjust from the unprotected microwave regime into the first into the double well regime, like a standard tunable flux qubit, and then to add on by suppressing the global alpha flux, additional 2-vortex hopping to get your dephasing protection. So we were able to confirm that with pulsed Ramsey spectroscopy here, here's a diagram of the type of experiment we do, where this bias pulse is now the 3 different types of fluxes that we have in the circuit, the local alpha, the global alpha, and the delta flux. And we can see that yes, the qubit is at least able to survive relatively not infinitely fast, but when the pulses are on the order of a few tens of nanoseconds, you can still see these oscillations. So the biggest proof of principle that we've done so far is just kind of show that that the qubit operates in a similar way to a tunable flux qubit. So when you pulse this local alpha, you basically are able to transition from the microwave regime over into regime where you now have your qubit state is in your double well. And once you're in the double well, you have a very, very long T1. It's also very easy just by tilting the well to essentially do a pi pulse. And so, and then bring yourself back out to this microwave regime and do the readout. And that's what's shown over here on the first on the bottom part of or I'll just do it on the top part, is that as you change the height of this local alpha pulse, you begin to see, or I should say that you do a large pulse, and then you come back part of the way, and then you delay, and then you go back the rest of the way, and then you read out. And so you can see that when you haven't gone, when your delay is happening in this double well regime, you get these very, very long T1 times compared to your reference microwave values. So
2-minute warning, David.
Sure. Yep. And the next step, obviously, is that we are working on implementing these changes in the global alpha bias, so that that hopefully will turn on, that will both simultaneously reduce the overall dephasing by kind of decreasing the inductive energy of the loop, but also turn on the double vortex hopping to provide the protection. So maybe there'll be some time to discuss some of the theory of this. I'm really looking forward to the discussion section. But again, I'd like to thank everybody that's participating in this conference and all the teammates. Thanks.
All right, we have maybe a little bit of time to take one question. Alexi, maybe you have a question? Oh, sorry, I apologize. That was a different one. So, okay, why don't we go on to Konstantin? Do you mind if you can, so David, do you mind if you can stop your presentation, and Konstantin, can you